Welcome back to Math 1910. We are still in the Algebra Review chapter. Alright, so it's chapter P. We're going through section 3. We're going to go through functions and their graphs. Alright, so we want to learn to use function notation. So we've done that before. Essentially, instead of saying y equals, we're going to say f of x equals. Alright, we're going to talk about domain and range. We're going to sketch graphs of functions. We're going to identify different transformations of functions. So for us, that's shifting left, right, stretching, shrinking, those sort of things. Okay, and then we want to classify functions and how to do composite functions and combinations of functions. Okay, so getting into function notation. All right, remember when we had like y equals 3x plus like 10. Y is a function of x, right? Where as x changes, y will be changed as well. So what we call x the independent variable, because that's the one that we can change. Y depends on what x is, so y is the dependent variable. So if I have 3x plus 5, all right, and I put x in as 2, I'm going to get 6 plus 5, which is 11. So y depends on x. The independent variable is the one where I can change all the values to, all right, and it impacts the output variable. Okay, so we're going to use that for function notation. So instead of saying like y equals 3x plus 5, we're going to say f of x equals 3x plus 5. It means the same thing, but it's going to be important when we start calculating things in calculus and being able to do our evaluations of functions and composite functions and things like this. Okay, so if we really just talk about y as a function of x, x is our independent variable and being changed, okay? And y is a function of x, so we write it as y equals f of x, meaning function of x. Okay, so we can write equations implicitly as well. This will be important when we do implicit differentiation later on in the next couple of chapters. Okay, but this is written in implicit form. All right, it's a standard form. We have x squared plus 2y equals 1. I mean, essentially, we're writing it not where one variable has not been solved for. Okay, we can still write this function in terms of y, but when it's written in terms of both variables, we call it written implicitly. Okay, so if we remember how to solve, we would get a y equals equation. Okay, so when we solve for y, we get y equals 1/2 times 1 minus x squared. So that's in explicit form. Why is it in explicit form? Because it is explicitly y as a function of x. So I'm going to step back aside. This is implicit. Okay, we have x and y mixed into our equation and it equals something. That's implicit. This one is explicit, means it's written in terms of a specific variable. In that case is y. So notice when we write things in terms of f of x, we just replace y with f of x. The equation does not change. Okay, so when we define things explicitly, that's going to say that y is a function of x. So we are going to say f of x equals 1/2 times 1 minus x squared. Okay, that's really just the difference between these. Okay, we need to remember how to evaluate a function. And example C here is very, very important. We are going to be doing a boatload of those in class when we do the definition of a derivative. But for the most part, why do we write function notations? So that we can substitute an entire quantity or an entire expression into another expression to evaluate it. So we're going to take this function f of x equals x squared plus 7, and we're going to evaluate it with examples a, b, and c. So we're going to substitute 3a in, we're going to substitute b minus 1 in, and we're going to substitute x plus delta x in. Okay, so you got to be very careful how we write this out. So for the first one, when we have a, we're going to write f of 3a, which means everywhere there's an x, so we're looking at the equation f of x equals x squared plus 7. Everywhere there's an x, we're going to replace that with a 3a. So that's going to become 3a squared plus 7. So that ends up giving us 9a squared plus 7 when we do that. Okay, so wherever there's an x, we're going to substitute it with 3a. So that's saying f of 3a. We're substituting that in for every single x value there is. Okay, so when that squares, that ends up giving us 9a squared. The 3 gets squared and the a's get squared when we simplify that. Alright, so let's look at example B now. We are going to replace every x in the original equation, f of x equals x squared plus 7, with a b minus 1. Okay, so we're going to replace every x with a b minus 1. There's only one x to replace, right? The x squared. So that gives us b minus 1 quantity squared plus 7. Now you have to remember it doesn't become b squared and negative 1 squared. You have to FOIL that out. So that becomes an entire polynomial there. So you have to take b minus 1 times b minus 1 to actually get the value there. Or recognize that you have to FOIL it out. So when you do that, you're going to get b squared minus 2b plus 1. That's just FOILing out the b minus 1 piece. And then plus 7. And then we simplify it down. Okay, so the final solution for that ends up being b squared minus 2b plus 8. So lots of homework problems on this. Example C, you really need to pay attention to. Okay, example C says that we're going to take f of x plus delta x minus f of x and divide it by delta x. So what we have to do is we're going to take x plus delta x and put it in for every x in the original equation, and then we're going to subtract the original equation and divide by delta x. So be very, very careful. This is a very important example. You need to be able to do this. Okay, so we're going to take that original equation, x squared plus 7, okay, and we're going to substitute in x plus delta x in for x squared. So we're going to get x plus delta x quantity squared plus 7 minus f of x. F of x is our original function, x squared plus 7. So we're going to replace f of x with x squared plus 7 and then divide by delta x. Okay, so let's just revisit that one more time. We wanted to find f of x plus delta x, so we had to take x plus delta x and substitute it in for the x into the original function. So that's why we have x plus delta x quantity squared plus 7. We replaced x with x plus delta x minus f of x, the original function, so we go minus x squared plus 7. Alright, and then divided by delta x. Don't forget that minus x squared plus 7, that negative in front of there, or that minus sign, distributes to both terms. We need to be able to do the algebra behind all of this. So you have to FOIL the x plus delta x. Remember, when we're squaring something, we multiply it times itself. So you have to do the binomial multiplication, or the FOIL there, or the box method, however you learned that, right? You're going to get x plus delta x times x plus delta x, which gives you x squared plus 2x delta x plus delta x squared when you FOIL that out, and then we have plus 7. Then we have to distribute the negative sign, so we get minus x squared and minus 7, all divided by delta x. This will work out if you do everything correctly. Alright, and this is just a preview of how we find a derivative, okay, using a limit approach. Now, notice what do we have in the numerator. We have an x squared and we have a negative x squared. Those will cancel. We also have a positive 7 and a negative 7. Those will cancel. Okay, so we can do some simplifying, and when we do those and those cancel, we're left with 2x delta x plus delta x squared divided by delta x. Now we want to end this with no numerator. Notice that there's a delta x and a delta x squared in the numerator. We want to end it with no denominator, sorry. And notice that there's a delta x and a delta x squared in the numerator. So I can factor a delta x out of the numerator. Okay, so when I factor a delta x out of the numerator, I'm left with 2x plus delta x, okay, times the delta x that I factored out, divided by delta x. Notice the delta x that I factored out in the numerator cancels with the delta x in the denominator. So my final, simplified version is 2x plus delta x. Okay. Later on, we're going to figure out what that is. Okay, and then we have to note that delta x cannot be 0 there because we would have division by 0. And remember, delta x is a change in x, but we're going to be calculating that on in a future chapter here. Okay, but we have to know that fundamental piece in order to be successful with our calculus part. Okay, all right, domain and range of a function. So we need to be able to understand that. Remember, domain is relative or is defining all the possible x values that function is possible. Range is defining all of the y values that function has as outputs. So if you can remember, domain is x, range is y, we're good so far. And then we have to look for where we have poles and zeros or asymptotes and those sort of things. Okay, so if we have this function right here, we should also know what? The domain and range of this function. Well, where are restrictions in the domain going to have issues? When we have division by 0. Alright, notice that if we plug in 2 or negative 2 here into this equation, 1 over x squared minus 4, if we plug either one of those in, we get division by 0. So those are going to be things that change our domain. So we're going to have asymptotes there. So when we write the domain for this set, we can say it's all x, and then quote, except for x cannot be plus or minus 2. So that's how we can say this and say that it is for all x. That's what so we have the brackets, we have the x with a quote. That's for all x except for x cannot be plus or minus 2. So that's how we can write the domain of that function there. Okay, so let's look at the next one here. We want to write the domain of this function. F of x equals the square root of x minus 1. Okay, notice if we put in 1, 1 minus 1 is 0. That's our 0 there. What happens if we put in negative 1? Then we start getting negative answers and we get imaginary answers. Okay, so we want to focus on the domain of the real part of this function. So the domain of this function is x has to be greater than or equal to 1, right? We can substitute 1 in because 1 will give us 0, which is a real number. Okay, but x cannot be anything negative. So x has to be greater than or equal to 1. It can't be 0 either, right? If we plug in 0, we get the square root of negative 1, so we get an imaginary output here. So a couple different ways we can write this. We can say the domain is x has to be greater than or equal to 1 because we can't include it. Or if you look at the bracket notation in the middle of the slide here, we can say the domain is from 1 to infinity. And we write that with a bracket, okay? A closed bracket, okay? That means we include the value 1. And then we'd go 1 comma infinity. And since it's infinity, it's not a finite value, that's where we have to have the parentheses. Okay, because that means we do not include the value. So remember, brackets, closed brackets mean we include the value. So it means when we use greater than or equal to or less than or equal to. And parentheses mean that we do not include that value, so that we use a parenthesis when we have infinity or when we do not include the value. So if we had like a less than or a greater than sign, we would use a parenthesis. Okay, so just to review, bracket goes with the greater than or equal to or less than or equal to sign. Parenthesis goes with the greater than sign or the less than sign. Okay, so if we take a look at the range, just looking at this graph, the smallest allowable value that is a y is a 0. And then it can go on to infinity. So the domain on this function goes from 0 to infinity. Those are all the y values. So everything above the x-axis. So we can say that the range, just to clarify, the domain, right, is 1 to infinity. The range is 0 to infinity, all of the y values. So we can say that y has to be greater than or equal to 0. That's an acceptable way to write the range. Or we can say that the range is on the interval 0 to infinity with a bracket next to the 0 and a parenthesis, all right, next to the infinity, as we see at the bottom of the slide there. Okay, let's take a look at the domain of tangent in the range. We did this in pre-calculus too, so we should know this. We did this in 1720. Okay, we should know, right, that tangent is sine over cosine, and we know that whenever cosine goes to 0, so at pi over 2 and 3 pi over 2, which is 90 or 270, all right, we're going to have division by 0 and we create an asymptote. So the range is really going to be affected here for tangent. So remember, tangent's going to go off of intervals though, because we're going around 360. So we can say the domain of tangent, as long as x cannot be pi over 2 plus n pi over 2, right? N's the integer since we're going around in a circle. So there's how we would calculate the domain of tangent, okay? Then the range of tangent we can obviously see goes from negative infinity to positive infinity, all right? So there's no issues with y, and remember that we can represent that with parentheses because we don't include the values, so negative infinity to positive infinity. All right, so let's talk about if, one-to-one, what did that mean? So one-to-one, okay, I'll read the definition here and then we'll kind of go through the function. From x to y is one-to-one when each y value in the range corresponds to one x value in the domain. So one x can only output one y. So that's a one-to-one function. Then we have a function from x to y is one-to-one if its range consists of all y. All right, so we, negative infinity to positive infinity on the range piece. Okay, but one-to-one, one x input creates only one possible y output when we want to talk about a one-to-one function. Just because it's not one-to-one doesn't mean it's a function, okay? But if it's one-to-one, one x produces only one y, okay? So we can take a look at this graph here. For every x value, there's only one possible y value, and it doesn't look like there's any limitations on y. There's no limitations on the range there, okay? You guys remember doing this? We can test to see if a function, or if a graph is a function, okay? We called it the vertical line test, okay? That checks to see if the graph is indeed a function. So what does that mean? I should be able to put a vertical line anywhere on that graph at any particular x value, and I should only get one possible y value. Okay, so 1x produces 1y using the vertical line test. Okay, so if I take a look at these graphs here, the graph on the far left is not a function because it doesn't pass the vertical line test. I can put a vertical line anywhere on that graph other than at the vertex there, all right, where it touches in multiple places. So the graph is not a function. Okay, then if we look in the middle graph, I can place a vertical line anywhere along that graph, all right, and it will only have one y value at that particular location. So that will be a function. It's okay here that it has, y values that are the same, but it's 1x can only have one y. Does that make, hopefully that makes sense here, okay? And then look at the last graph. I can place a vertical line anywhere on that graph, and there will only be, or it'll only touch the graph once. It doesn't matter if they don't exist, right? It doesn't look like the graph exists from 0 to 2, but that's okay. It's not sharing any values, so it is a function. So you can always use the vertical line test to see if a function is a function, okay? Now, we look at our 8 basic parent functions here, and these are the majority of the functions that we will deal with in calculus, okay? We should know the first function, right? It's a line. It's linear, okay? The parent function is f of x equals x. We should know the next function as a parabola, right? A squaring function. We should know exactly that the parent function is f of x equals x squared, and we should know what happens when we shift any one of these up, down, left, right. We scale it up, scale it down, do those sort of things. We translate those, okay? Then we have the cubic function, f of x equals x cubed. We have a square root function, all right, so some form of x equals y squared. We have an absolute value function, all right, that's always going to produce a v for us. We have a rational function. Anytime we have 1 over x, it will always create a parent function of that graph. And we should know sine and cosine from taking pre-calc 2 or 1720 class, okay? So you need to make sure that you know and memorize what all 8 of these look like, all right? We're going to be using them throughout calculus all the time. And if you understand the parent function, it'll help you understand if you're right or wrong on future problems that you're working on. All right, this should be review as well. We should understand how major transformations work. So we're going to do the example here with the y equals x squared as the parent function, and then we're going to see what happens to the parent function when we rewrite it. So if we look at the graph all the way left, how do we do a vertical shift? It can be up or down, right? So we can take x squared plus 2, that's what's shown there, or if we went minus 2, it would drop down 2 units below the x-axis. So remember, a vertical shift, it stays outside the x squared, okay, and we're able to move it up or down. Now a horizontal shift to the left, remember these are opposites, okay, so we have to rewrite it a little bit differently. So notice that y equals x squared now becomes some sort of binomial squared. So in this case it says x plus 2. Notice the graph is shifted left 2 units. Why? Because negative 2 plus 2 creates 0. And that's where the graph has to cross the x-axis. So if we add, it shifts it left. If we subtract, it shifts it right. If this was x, if we shifted it to the right 3 units, it would be x minus 3 quantity squared. Okay, so understand when we're shifting up and down, there's no parentheses, and the plus or minus is on the outside of the x squared. If we're shifting left and right, a horizontal shift, notice whatever that shift amount has to be inside parentheses. We have to do a quantity there. Okay, remember how to reflect the graph. If it's positive, it should be vex. If we put the opposite in front of it, it makes it concave with this, so it reflects it when it's the opposite. Okay, and then we should be able to write out an equation that understands how we, shift it up, and then reflect it down, and then we shift it left 3 units. So you should be able to, look at that graph and see what happens. We have to know, all right, it flipped, so we got to have a negative f. We know it's shifted to the left 3, so we have to have plus 3, and we notice that the graph shifted up 1, so we have to have a positive 1 in front. So you should be able to do all these different transformations to a parent function that we have. Okay, very, very important. We should be able to do vertical shifts, horizontal shifts, and reflections about it. Okay, so original function here, and this is just what we just went through in the last example here. We're just writing it out so that you understand what the vertical shift looks like. Okay, where it's outside, inside, makes it go left and right. When it's reflected, how to combine them all into one. Okay, so this is the general, terms for shifting just a function in general. So this could work for, a cubic, anything that's linear. It still applies to whatever we're working on. Okay, and then we talk about how to reflect it. And notice the reflection there. If the negative is on the outside, it reflects across the x-axis. If the negative is on the inside, it reflects across y. And if it's a negative on the outside and the inside, it reflects about the origin. So we should know how to do this. This should be reviewed from your conics section from your Algebra 2 class and things like that. All right, so understanding and classifying functions. So elementary functions for us, there are 3 categories. There's algebraic, trigonometric, and exponential and log functions. Okay, those go hand in hand. So algebraic for us, right? Polynomial, radicals, rationals, things like that. Trigonometric functions, we spent a whole semester in 1720 on that. Sine, cosine, tangent, cosecant, secant, and cotangent. Okay, and then exponential. So we're talking like, e to the x, or natural log functions, ln, or log functions, log. Okay, anything 2 to the x, exponential, those sort of things, growth and decay. You talked about those. Okay, so the most common function we always deal with is called the polynomial. You should know that. That's kind of the formal definition of how a polynomial expansion looks like. All right, but we know that the numbers in front of the variables are called the coefficients. Okay, and we have a leading coefficient, which is the an, so that's the one with the highest exponent, and then we have the constant term, that's the one at the end. Okay, and then n is always the degree of the polynomial. So if it's x to the third, the n would be 3, and that would be a third degree polynomial. Okay, so basic understanding of this, a 0 degree would be f of x equals a, where a is a constant. There is no x value. So, right, because x to the 0 is 1, so that's why it's 0 degree. If we have a first degree polynomial, it's a line. We have a x to the first plus b, right? Second degree polynomial, we have ax squared plus bx plus c. Third degree, right, ax cubed plus bx squared plus cx plus d. So we can see, all right, the degree is the highest exponent on the polynomial. Even if we don't have anything else, so even if we had just like 10x cubed, it would still be a third degree polynomial. All the other pieces would be sitting at 0. Okay? So understanding, even in odd functions or things like that, an, okay, that's the leading coefficient and how this affects things. Okay, so if we have an an greater than 0, okay, our function might look like the one on the left. Now that's something to potentially the fourth. Okay, if our an is less than 0, we should be going down. Okay, and it depends on the function though, because the function is even for those. Okay, so if we cut this in half, the first function on the far left hand side, that's probably something to the fourth, potentially. Okay, it's an even function. The second graph, okay, that's a parabola going down. So what we need to understand is, if we have an even function, so something with a power of 2, 4, 6, 8, 10, 12, 14, 16, so on and so forth. If an is greater than 0, both ends will be pointing upwards. If an is less than 0, okay, both ends will be pointing downwards, where an is the leading coefficient on the polynomial. The two graphs on the right, okay, those are for odd functions. So, or not an odd function, but the odd degrees, all right? So if we have, x cubed, x to the 5th, x to the 7th, x to the 9th, x to the 11th, so on and so forth. If an is greater than 0 in that case, it's going to have down on the left and up on the right. If an is less than 0, it will be reflected. It will be up on the left and down on the right. So those are kind of the rules, okay, for the leading coefficients on our polynomials here. And if we have an odd exponent versus an even exponent, or power is really, kind of what we're talking about there. All right, so if we do something called the leading coefficient test, that's only telling us the left and right behavior. I'm going to step back a slide. Leading coefficient test, left and right end behavior. So where does it end on the left-hand side of the graph versus where does it end on the right-hand side of the graph? And this is what we just talked about here. All right, with both ends pointing up, both ends pointing down when it's even. All right, or one's down, one's up, or one's up and one's down, like we did here with the odds. So that's really talking about the leading coefficient test. We're only talking about the end behavior of the function, okay? So we can also talk about rational functions, okay? That's really just the quotient of two polynomials. Remember, quotient is a division, all right? So if we have f of x equals p of x over q of x, and they're both polynomials, okay? And moving on, we need to talk a little bit about transcendentals. Transcendentals are functions that are not algebraic, okay? So trig functions are transcendentals. Does that make sense? Sine, cosine, they're not algebraic. There's algebra rules that can apply to them, all right? But transcendentals are functions that are non-algebraic, okay? So we have function classifications and doing combinations of functions. All right, we can have two different functions, f of x, g of x, h of x, all those different kinds of things. In this example, we're going to take f of x equals 2x minus 3, and we have g of x equals x squared plus 1. So if we write a sum, right, it's going to give us f of x plus g of x, so we can combine like terms if we have any. So we can say that f of x plus g of x, if we take those using the f and g that are given above, all right, we can end up with 2x minus 3 plus x squared plus 1. All right, and if we wrote all that out, we would have x squared plus 2x minus 2. We could combine some of the like terms. Difference is just subtraction. You got to remember, this is all review, guys. If you multiply them, you should get the product, quotient, division. Okay? So those are just being able to do simple mathematical operations with two different functions. Okay, and those create composite functions. Okay, remember, composite functions are where we have functions inside of functions, or we combine multiple functions and things like that. Okay, so if we have composite functions here, another way we do this is where we have a function inside of another function We did this a little bit in pre-calc 2, where we have f of g of x. That is not multiplication, where it looks like the word fog. That's f of g of x. So that means I am taking g of x and putting it into f of x. That's kind of like what we did at the beginning of the lecture here, where we had to put like 3a when we evaluated 3a, or when we evaluated b minus 1, or when we evaluated, you know, x plus delta x minus f of x all over delta x. When we evaluated those, that's kind of a composite function for us. So f of g of x, I'm going to take whatever g of x is, and I'm going to substitute it in for the x in the f of x function. Okay, so we say f of g of x. So we want to find each composite function here. So we have f of g of x. Okay, that's the first one. So what we're going to do is we're going to take g of x and put it into the x in f of x. So when we do that, okay, it's going to look like this. We're really going to take g of x is cosine of x. So now we're going to take cosine of x and put it into the 2x minus 3 function there. All right, so we're taking g of x and putting it into f of x. So wherever there's an x, we're going to replace that with cosine of x. So our final simplification becomes 2 cosine of x minus 3. So that's f of g of x. Then we want to go the other direction. We're going to find g of f of x. So I'm going to take f of x and substitute it into the g of x, okay, in this case. So I'm going to take f of x, which is 2x minus 3, and I'm going to put it into g of x. So that becomes cosine of 2x minus 3 when we work that out, okay? So notice, okay, important, f of g of x does not necessarily equal g of f of x, okay? All right, moving forward here, we talk about an x-intercept. We did that last lecture. You know how to find the x-intercepts. You should know how to find them. We also call that the 0. Where we cross the x-axis, it's called the 0 because that's where y equals 0. But we call those intercepts as well. Okay, so if we look at this function here, we have f of x equals x minus 4. Okay, it has a 0 at 4 because if we substitute 4 in, 4 minus 4 is 0. The best way, right, to find these, if you remember, we take the piece, so we take x minus 4, set it equal to 0 because that's when y is equal, and solve for x. When we do that, we get x equals 4. So you can, you know, solve these visually or algebraically when you go through them. All right, we want to test if a function is even or odd. All right, so the way we do that is if we plug in or substitute in a negative x and we get the same equation back, the function is even. If we substitute in a negative x and we get the opposite function back, it's an odd function. Okay, that's really all you're doing. You're not even substituting in a numerical value. You're substituting in a negative value of the opposite value of x into the function and see if you get it back. It's kind of like when we tested for symmetry for about, you know, the y-axis, the x-axis, and the origin. Same kind of thing. We're just substituting in an x value here. So we want to determine if the function's even, odd, or neither, then find the zeros of the functions. So we're going to do this with two functions here. We have f of x equals x cubed minus x, and we have g of x equals 1 plus cosine of x. So first, we got to see if it's even or odd. So I'm going to take a negative x and substitute it into each x in equation A. All right, so we're going to end up with negative x cubed minus a negative x. All right, and then when I simplify that down, I cube a negative x, I get negative x cubed. And when I use negative times negative as a positive, so I end up with getting negative x cubed plus x. And then if I factor out a negative, okay, I get negative quantity x cubed minus x. So I get a negative f of x back. So that tells me that what? I get the opposite of f of x back, so the function is odd. Okay? And then if we want to find the zeros, all right, I'm going to factor an x out of this. I have x cubed minus x, and this is stuff I think we did in the first or second algebra review lecture. All right, we're going to factor out an x there and be left with x times x squared minus 1. And we know x squared minus 1 is the difference of two squares, so we're going to be left with x times x plus 1 times x minus 1. Okay, and then we set that equal to 0. So we're going to have x times x squared minus 1 times x plus 1 equals 0. we're going to take each one of those values and set it equal to 0 and solve for x. So we're going to set x equal to 0, x minus 1 equal to 0, and x plus 1 equal to 0 and solve for x. When we do that, we get a 0 at 0 because x equals 0. And then when we solve the x minus 1 equals 0, we get x equal to 1. And when we solve the x plus 1 equal to 0, we get x equals negative 1. So the zeros of this function are 0, 1, and negative 1. Okay, and if we were to look at the graph, all right, we know it's a cubic. All right, and if we look at the end behavior, it's going from negative infinity to positive infinity. Okay, let's look at the next function. All right, it was 1 plus cosine of x. So we are going to substitute a negative x in to see if it's even or odd. Okay, so what we need to do is do that. So we're going to do 1 plus cosine of negative x. So when we do that, we realize that no matter what, cosine of negative x is still the same thing as cosine of x. So if I put in cosine of pi, what's cosine of pi? Negative 1. Well, what's cosine of negative pi? It is also negative 1, right? I've just gone the other way. So that's really essentially, what you're getting when you do that. So if we end up doing this, we see that the function it's an even function, okay? So now we have to find the zeros. We have to take 1 plus cosine of x and set it equal to 0 and solve. So we get cosine of x equals negative 1. Well, where are the answers? When is cosine of x negative 1? Well, we should know that that happens when what? Cosine is pi. And then it happens for every single variation of pi. So as it goes, every time that it goes around, it gets to pi. Okay? So that's how we do that. So it would be what? 1 pi, 3 pi, 5 pi, 7 pi, 9 pi, so on and so forth. Okay? It's an even function, so there's how we would, find that. And if we were to graph, we should know what the graph of cosine looks like. It's just cosine, and it's raised up 1. Okay? Alright guys, well that's it for this lecture. As usual, email me with any questions or anything like that. Else guys, have a great day, and I will see you in class.